dot plot. All right, now we're actually getting to the stuff. So we can add, subtract vectors. We can multiply by a scalar, right? We can do expressions. Now, how do we multiply and divide? Well, we can't really divide vectors, which is kind of funny, but we can multiply. So that is called the dot plot, multiplication. So given two vectors, A and B, the dot plot or dot product is just literally just the multiplication of two vectors put together, okay? And it's funny because it's the exact same way we add. Instead of adding x components, y components, and z components, we literally just multiply and then call it a day. However, instead of actually being a component, we actually get a number out, which is pretty interesting. Okay. So the dot product actually gives you a value out instead of just another vector. Okay, that's a key thing. Now, one very, very interesting thing about the dot product is this one right here. Okay. So the dot product actually gives you the length of the vector squared. Okay. So remember, if you're squaring it, it takes rid of the square root. So you just get what's inside the square root. Okay. So this just has to incorporate just a dot a. It could be just right here. So let's say, for example, vector a times vector b, or the dot product of vector a and b, is the same as the length squared. Which is also very interesting. So just be worried about that kind of stuff. Once we go into proofs, this actually gets a really big thing when it comes to it. Okay. All right. So the question now becomes, okay, we know how to do dot product. Okay? You got to multiply, good. But does it do anything to us to help us each other out? Meaning, does it have any significance in vector space? Okay, so let's find out. So we have a regular old space here. And let's say we have one vector A going this way. Say this is A. And let's say one vector going this way. We have vector B. And now we know that if I subtract A minus B, we end up with our triangle here. Now, we have this special property, right? And if we just do A dot A, so the dot product of A but with itself, we know we just get its length of just A, right? So the length of, besides the square root. So that gives us a number. Let's call that, here's our length A. And if we do the same thing for B, so B dot product, it's B itself, we also get the length of B completely. Okay. Well, interesting thing is, if I connect these two together, that kind of looks like an area. Huh. Well, we could be onto something. Okay. So maybe the dot product helps us do some type of area in 3 dimensions. And in fact, and actually not fully, but it's a brief, nice precursor to what we're going to be talking about later on in the course called the cross product. Now, we're not really done because we know if this is a 90-degree angle, we have a rectangle, pretty much, right, if we put everything around. But if this is not a 90-degree angle, then we get something called a parallelogram or vice versa, because these are now straight lines. So if I go back here, this angle being represented is this angle here, theta. So that theta is actually pretty important. So really, a better explanation or better definition of what the dot product represents and what physicists actually use it for is this equation down here. Okay? So this is all fun and dandy, but most of the time when we talk about dot product, we're using this equation here. So the dot product is basically the dot product A to B is the multiplication of A, the length of A times the length of B times the cosine of the angle given to us between vector A and vector B. And again, that angle represents from right there. So the special case is if the angle is a right angle, so literally is on the x scale or the z scale, we literally just get a rectangle. So we can find the length of that particular rectangle in three-dimensional space, which is also pretty interesting. So now that we have a new equation, let's practice it two different ways. Okay. All right, first, find the dot product AB when vector A has length 6 and B has length 10. So basically, we have no other choice to use this one because we don't know the components of A and B, so we can't use our basic dot product proportion. We have to use its better definition. And the angle between them is pi over 6. All right. So using our equation, so the length of A, so A dot B is equal to the length of A, which is 6, times the length of B, which is 10, and then cosine the angle between them, which is cosine of pi over 6. Okay. All right. So that's just going to give us 60 times pi over cosine of pi over 6. Which means cosine of pi over 6. Let's see, what is that? It goes 3, 2, 1. So square root of 3 over 2. Which just simplifies to 30 radical 3. All right. So now that we have that, let's do a little more difficult one. So find the angle between vector A and vector B. Okay. So there's a couple ways of doing this. Well, actually, one or two ways. I'm going to do the most direct way. So we want the angle here, right? So in other words, we need everything else. Okay. So we actually have to use both definitions to help us out because we don't know the dot product of each one. We can't find it and we can find the length of each one itself, right? So it's going to be a pretty lengthy problem itself. So let's first start with the first one, the dot product. So let's first find A dot product B. And remember, all that is just multiplying each components together and then just adding them up. So that's just going to give you 5 times 2 is 10, plus -3 times 2 is -6, plus 0 times -3 is just 0. So this gives us 10 plus -6 is 4. So the dot product of A and B is 4. So check, we got this. So we know 4 equals something. I'll just do this for sake, right, in an equation. So next we want to find the length of A and B individually. So the length of A is the square root of each component sum squared, right? So 2 squared is 4, another 2 squared is 4, -3 squared is 9, So 4 plus 4 is 8, and then 8 plus 9 is 17. So the length of A is the square root of 17. And then do the same thing for B. So 5 squared is 25, negative 3 squared is 9, and 0 squared is just 0. So this is the square root of 34. Okay, putting stuff together. So b4 is equal to, if you notice, I can rewrite square root of 34. I'll just put it to the side here. As square root of 17 times square root of 2. And 17 times square root of 17, they cancel. So we just get 17 radical 2 to simplify. Just makes stuff a little easier to look at. And we just want to solve for theta, meaning, right, we divide everything by all this. So we get 4 over 17 radical 2 equals cosine theta. And let's see if you guys remember your trig and mostly your trig. How do we solve for theta? Anybody remember? Or another way, how do we get rid of this cosine attached to this theta? Yeah, inverse. There you go. You got it. So we have to take inverses of both sides. So it'll be cosine inverse of 4 over 17 radical 2 equals theta. So this you actually need a calculator for. But again, most times they're going to say just without a calculator, just give me what it actually is. But you know, just for practice sake, I know a lot of people really need their calculator to do so. So why don't we just do that real quick? Where's my calculator? No, here it is. Actually, before I go any further of this stuff, one thing way back in pre-calculus, you probably really forgot. It's been a while. Make sure your calculator is in degree because you want a degree out. Okay. Remember, in radians and degrees gives you different answers. So because we want a degree out, make sure your mode is in degrees in your calculator. Because if you get radians, you get something drastically different instead of the actual degree itself. Okay. So the angle between vector A and vector B is approximately 80.4 degrees. That's what I got. So before going any further, any questions on using our new equation of the dot product to solve for values? No? All good. And as you can tell, right, it's a simple equation, right? I can given 1, 2, 3, 4 unknowns, given 3, find the other one. It's pretty straightforward. So there's multiple questions I can ask based off that. And you would do the same thing, right? Plug and chug, find the parts that you have and solve for the part that you're missing, right? I'm pretty sure this is the lengthiest because you just have to remember you have to do cosine inverse of it, but still not that difficult to do. Okay. All right, orthogonal. Okay, so orthogonal vectors. So 2 or more vectors are orthogonal if they are perpendicular to each other. Okay. Or in other words, the angle is equal to pi over 2, right? So 90 degrees or pi over 2 means orthogonal, right, perpendicular to each other. So a very important one is, in other words, the dot product equals 0. That's the key thing. So 2 vectors are orthogonal if the dot product equals 0. Okay. So let's try this example out. Find two non-parallel vectors, both orthogonal to the point 1, 1, 1. So we'll call this vector A for short. And in other words, basically, we want to find two other vectors or two other points, right? Because we're not given any terminal points. So we consider our terminal point as 0, 0, 0, that are orthogonal to this point here, but also non-parallel to each other. Well, let's go back to what we know. We know two vectors are orthogonal if the dot product equals 0. So in other words, A dot B is X plus Y plus Z equals 0. Now, if you're wondering why they equal X, Y, and Z, is let's suppose vector B1 is just the vector X, Y, and Z. Right? So therefore, we do the dot product of that. X times 1 is just X, Y times 1 is Y, and Z times 1 is Z. There you go, if you wonder where that came from. Yeah. So therefore, all we have to do is figure, okay, what combinations would give us 0 if I would add X, Y, and Z up? So for example, if Y is 2, and let's say X is 0, what does Z have to equal to make this true? So if I just put 0 plus 2 plus Z gives us 0. Oh, ooh, there we go, come on, back into focus. There you go. Come on, focus, focus, focus. There you go. Oh yeah, there you go. So we got -2. So our first point, or our first vector, would be 0, 2, and -2. Since we're on vector notation, there's B1. Ta-da. But since we wanted 2 of them, well, okay, let's find another one. Well, that just means I just pick another situation. So going back to our general, pick another one. So anyone, give me any number for X. What you guys will like? Give me any, what's your favorite number? First one I see I pick. 8. All right. So actually, we'll do 8 and 23. So if X is equal to 8 and Y is equal to 23, or actually, let's do the opposite. So if X is 8 and Z is 23, well, what does Y have to give me to get 0? There we go. So our other point would be 8, comma, -31, comma, 23. And they're non-parallel, right? Which is the best part. So you can give me, infinite number of vectors that are non-parallel to, or sorry, that are orthogonal to this value just based off that scenario. So something that's, and like I said, this is the most difficult part of this class is, this is a very small example, right? But, just getting started of it sometimes gets the difficult part, right? Going back and figuring out what does this mean? What does that mean? Okay, what are they trying to tell me here in itself? And just knowing a lot of the times you go back to a general vector or general stuff, right? So most of it is just going to be, obviously we're going to have numbers involved, but most of it is just going to be surfaces and in the general format where you have X, Y, Z, right, as an actual point itself. So just be careful, just don't be careful of the notations. That's the reason why, homework is very crucial. Be comfortable. And I try my best to give you guys homework that is kind of along the lines as I teach you here with a little bit of a twist. So every so often I give you guys one, That's a little hard, and I'm not going to lie. Just to give you guys some practice of what you can be seen on tests and quizzes itself. Okay. You know, just a little fun example, I call them. All right. So almost last part. We're almost finished. Don't worry. The last part of this is called the directional angles. So the directional angles of a vector are the angles alpha, beta, and gamma that the vector makes with the x, y, z axes in 3 dimensions. Okay, so these angles are considered as cosine theta is equal to the component of a1 over the length of a, and vice versa, right? It's pretty straightforward. So again, that tells you the angle at which the vector is going for every single one. So if you guys want an example of what I mean by that, x, y, z. So given like a vector here, this is going to be hardest to do. So let's say, well, this is my vector A. So this angle here would be gamma. This angle here would be beta. And this angle there would be alpha. Again, going just straight to the x-axis itself. Okay. All right, so again, just since we're given an equation, let's do a bit of practice to figure out how we would use this. So find the directional angles of the vector a equaling 2, 2, negative 3. So first off, we're going to have to find the length of it no matter what, or the magnitude. So 4, so 2 squared is 4, 2 squared is 4, and then negative 3 squared is 9. So this is square root of 17. So then cosine of alpha is equal to the first component, which is 2, over the square root of 17. Cosine beta is equal to the same thing. And cosine gamma is equal to negative 3 over the square root of 17. And then since we want the angle, so just like last time, we have to do cosine inverse of both sides. There we go. So usually I would leave it like that, but just in case you really want to find the exact values, I'll do it for you guys. So alpha, we approximately, I'll just go to the nearest degree, 61 degrees. So beta is the same. And then gamma. And there we go. Great. Any questions there? Yeah. So to finish up this section, we go over to 2 types of projections. Something called a vector projection and a scalar projection. So a vector projection, the funny thing is, if you look at the pictures themselves, you see what is the actual difference between them. But there's actually a big difference between them. So just a fun little fact there. So let's suppose I have these 2 vectors here. I have vector A and then vector B. Okay. So a vector projection basically means is I make a line, perpendicular line from its terminal point down to A itself. This is what's called a projection. So you can kind of think of it as a shadow. So like basically, what does the shadow make to this? So this is going to be our new vector right here. That already. So this vector here, in blue, would be our projection vector. Or what does the shadow create itself? It's actually did. So that's called a vector projection. A scalar projection, again, it's going to look exactly the same picture. Just give me a sec. Okay. Okay. So a scalar projection is if I would get this vector and literally put it right on top of A. Okay. So instead of a shadow or just a projection of it, so literally just looking at what the shadow would look like, this is the magnitude or the length of B of B onto A. So if I literally just put it right on top of each other, that's the key thing. So if I want, I made two big pictures, but basically, if I just put them right on top of each other, I have A being the big one, and then B being here. That's literally what's happening when it comes to a scalar projection. They lay them right flat at each other, and this length here is that. Now, you may say, well, that doesn't make sense because we could just find the length of B and call it a day. Okay? Yes, but because it's the length of B, we have something very important. This angle here also makes a big difference of it. Because, well, sometimes if you're not given the length of B, how do you find the projection of it, portion? So if you noticed, we have a right triangle. And so all those love stuff when it comes to cosine, sines, and all that fun stuff comes into play here. But the good thing is, we always care about that length there. So we'll always be using the sine of it this time. Yeah. So, and that goes back to our last types of equations here. So a scalar projection of B onto A, we call it composite or COMP, is a dot product divided by the length of A, or the vector projection. So the first part was as a shadow, is a dot product, again, over the length of A squared times, again, the vector A. Okay, because again, since we're dealing with, remember, scalar projection is the length of A, so the vector projection is just that kind of stuff itself. Okay. All right, so in this case, why don't we finish up this section with a couple examples and then call it a day there. Okay. So we want to find both projections, so the scalar and vector for both each one itself. Okay. So we'll just do with the scalar since it's a little easier, and that pretty much gives us the projection itself. So first thing we gotta do is we gotta find the dot product of A and B. So multiply. So hopefully at this point I can skip a couple steps but I'll just say it as I go. 5 times -2 is -10. -3 times 7 is -21. And then 7 times -3 is also -21. So what is this? -42 plus 10, so -52. And now we got to find the length of A. And the good thing is only the length of A, which is nice. So length of A, which is right here. So 5 squared is 25, -3 squared is 9, and 7 squared is 49. So, what is this? 9 plus 25 is 34. And 34 plus 49. You guys can tell me if my math's wrong. Is it 83? I think that's 83. You guys will tell me. No, we'll just assume it's 83. And then since we want the portion, so the length squared is going to be 83 as it is. Yeah. Oh, yes. Cool. All right. Now we have everything we need to find both of them. So the scalar projection, so the comp of B onto A, so vector B onto vector A, is the dot product. So -52 divided by the length of A, which is the square root of 83. Done. Perfect. Right, that's the easier of the two. Okay. So next we do the vector projection. So the vector projection is the projection of B onto A. So again, that's the dot product. So -52 divided by, it said, now it's going to be 83 times the vector A itself. Okay. So times that. So we just so vector A here. So just to get you guys accustomed to the notation, I'll write it as I, J, and K. So it'd be negative. Well, actually, we're multiplying, right? So that's right, we're multiplying. Sorry, give me one sec. Where's my calculator? So -52 times 5. And I'm not going to be simplifying, so just in case you guys are wondering, I'm just going to quickly just go through it. So -260 divided by 83i plus 3 times 52, positive 156 over 83j, and then minus 364 over 83. Okay. Yep. So those are our two answers there. So those are scalar projection and our vector projection. Any questions there? So let me leave this up while I do the next one here. All right, so just do one more just for practice sake, right? Like I said, I usually like to do 2, maybe 3. You could be guys, all right, 1, I'm kind of iffy, just go through the motions. 2, okay, I kind of understand where goes where, and then 3 is like, all right, I get it now when it comes to it. So let's do the same thing, the projection from B onto A. So just like we did last time, we need A dot B. So this is going to be -2, 3, and positive 21 this time. So this is 1, so 22. The length of A. So 1, 3 squared is 9. This will be 49. is equal to the square root of 59. And then therefore the length of A squared is 59. Yeah. So first we'll do the scalar again. That's the easy of the two. And that's going to be 22 divided by the square root of 59. And then the projection will be 22 divided by 59 times vector A. So this will give me, here's vector A, doing that. Yeah. All right.